Have you ever looked up at the night sky and wondered what it all means? The universe is vast and mysterious. It's full of stars, planets, and galaxies. But what are these things made of? How do they interact? These are some of the biggest questions in science. To understand the universe, we need to look at the smallest things, atoms. These tiny building blocks are the foundation of everything we see around us. From the vastness of galaxies to the intricate details of a flower, it all starts with atoms. Inside these atoms we find even smaller particles, such as protons, neutrons, and electrons. These subatomic particles are the true essence of matter, and they hold the secrets to the universe's most fundamental properties. Everything we see, touch, and experience is made of these tiny particles. They come together in countless combinations to form the diverse materials and objects that make up our world. From the air we breathe to the stars in the sky, it's all a complex dance of particles. These particles are not static. They move and interact according to the laws of physics. Their behavior is governed by principles that scientists have spent centuries uncovering. These interactions are what give rise to the properties of matter, such as solidity, fluidity, and even the ability to conduct electricity. The laws of physics also govern the forces that act upon these particles, such as gravity and electromagnetism. Gravity pulls objects towards one another, while electromagnetism governs the interactions between charged particles. These forces are essential for the structure and behavior of everything in the universe. However, there's a problem. The laws that govern the very small, known as quantum mechanics, don't seem to fit with the laws that govern the very large, known as general relativity. Quantum mechanics describes the strange and often counterintuitive behavior of particles at the smallest scales, while general relativity explains the force of gravity and the structure of space-time on a cosmic scale. This is where string theory comes in. String theory is an ambitious framework that attempts to reconcile these two sets of laws. It suggests that the fundamental particles we observe are not point-like dots, but rather tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe. If string theory is correct, it could provide a unified description of all the forces and particles in the universe, bridging the gap between quantum mechanics and general relativity. Imagine a universe where everything, from the smallest particle to the largest galaxy, is made up of these tiny, vibrating strings. This elegant idea has the potential to unlock new understanding of the cosmos and answer some of the most profound questions in physics. While string theory is still a work in progress, it represents a bold step towards a deeper understanding of the universe's fundamental nature. Scientists around the world are working tirelessly to test the predictions of string theory and other theories that seek to explain the universe at its most fundamental level. Through experiments and observations, they hope to uncover the true nature of reality and the underlying principles that govern everything we see. As we continue to explore the universe, both at the smallest and largest scales, we are constantly reminded of the incredible complexity and beauty of the cosmos. From the tiniest particles to the vast expanse of space, the universe is a tapestry of interconnected phenomena, all governed by the same fundamental laws. The journey to understand the universe is far from over, but each discovery brings us one step closer to unraveling the mysteries of existence. By studying the tiniest particles, we gain insights into the grandest structures, and in doing so, we come to appreciate the profound interconnectedness of all things. Imagine the universe is like a giant symphony. Each particle is like a different musical note. String theory says that these notes aren't actually points. Instead, they're tiny vibrating strings. Just like different vibrations of a violin string create different notes, different vibrations of these fundamental strings create different particles. One of the most exciting things about string theory is that it could unify all the forces of nature. This idea has captivated the minds of physicists for decades, as it promises to bring together the seemingly disparate forces that govern the universe into a single, elegant framework. Right now, we have separate theories for gravity, electromagnetism, and the strong and weak nuclear forces. Each of these forces operates under its own set of rules and equations, making it challenging to understand how they might be connected. Gravity, for instance, is described by Einstein's theory of general relativity, which explains how massive objects warp the fabric of space-time. On the other hand, electromagnetism, which governs the behavior of charged particles, is described by Maxwell's equations. String theory suggests that these forces are all just different aspects of one fundamental force. According to this theory, the fundamental building blocks of the universe are not point particles but tiny vibrating strings. These strings can vibrate at different frequencies, and the different modes of vibration correspond to the different particles and forces we observe. In this way, string theory provides a unified description of all the forces of nature. Think of it like this: electricity and magnetism used to be considered separate forces. For a long time, scientists thought that electricity and magnetism were unrelated phenomena. However, in the 19th century, James Clerk Maxwell developed a set of equations that showed how electric and magnetic fields are interrelated. This was a groundbreaking discovery that led to the unification of electricity and magnetism into a single force, electromagnetism. Now we understand they are two sides of the same coin, electromagnetism. This unification was a major milestone in the history of physics, as it revealed a deeper underlying connection between what were once thought to be separate forces. Similarly, string theory aims to reveal the underlying connections between all the fundamental forces of nature. String theory aims to do the same for all the forces. By proposing that all particles and forces arise from the vibrations of tiny strings, it offers a potential pathway to a theory of everything. This would be a single, all-encompassing framework that describes all the fundamental forces and particles in the universe. If successful, string theory could revolutionize our understanding of the cosmos, providing insights into the nature of space, time, and the very fabric of reality itself. The mathematical elegance of string theory is one of its most appealing features. The equations that describe string theory are incredibly complex, yet they have a beauty and symmetry that suggests they might hold the key to unlocking the mysteries of the universe. Physicists are drawn to this elegance as it hints at a deeper, more fundamental truth about the nature of reality. Despite its promise, string theory is still a work in progress. Scientists around the world are working tirelessly to develop and test the theory, seeking experimental evidence that could confirm its predictions. This is a challenging task, as the scales at which string theory operates are far beyond the reach of current experimental techniques. However, advances in technology and new theoretical insights continue to push the boundaries of our understanding. Experiments at facilities like the Large Hadron Collider are helping to probe the fundamental nature of particles and forces, providing valuable data that could one day support or refute string theory. These experiments are crucial for testing the predictions of string theory and for exploring the frontiers of particle physics. The journey to unify the forces of nature is far from over, but the potential rewards are immense. A successful unification would not only deepen our understanding of the universe but could also lead to new technologies and applications that we can scarcely imagine today. As we continue to explore the mysteries of the cosmos, string theory remains one of the most promising avenues for achieving a unified theory of everything. String theory could also help us understand some of the most mysterious objects in the universe, like black holes. These enigmatic entities have puzzled scientists for decades, and string theory offers a new lens through which we can examine their complexities. These are regions of space-time where gravity is so strong that nothing, not even light, can escape. The immense gravitational pull warps space-time itself, creating a point of no return known as the event horizon. Once something crosses this boundary, it is lost to the black hole's insatiable appetite. String theory suggests that black holes might be even weirder than we thought, possibly connected to other universes through things called wormholes. These hypothetical passages could act as shortcuts through space-time, linking distant parts of our universe or even different universes altogether. Imagine a tunnel that could take you from one galaxy to another in the blink of an eye. Some versions of string theory even suggest the existence of a multiverse, where our universe is just one of many. In this grander scheme, each universe could have its own unique laws of physics and constants, making them vastly different from our own. The idea of a multiverse challenges our understanding of reality and opens up a realm of possibilities that are as fascinating as they are mind-boggling. Imagine a cosmos where every decision you make spawns a new universe, each with a different outcome. In one universe, you might be an astronaut exploring the stars, while in another, you could be living a completely different life. The multiverse theory suggests that all these possibilities exist simultaneously, each in its own separate universe. Scientists are working tirelessly to understand these concepts, using the mathematical framework of string theory to explore the fundamental nature of reality. String theory posits that the basic building blocks of the universe are not point-like particles but tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe. The vibrations of these strings determine the properties of particles, much like how the vibrations of a guitar string produce different musical notes. This elegant idea has the potential to unify all the forces of nature, from gravity to electromagnetism, into a single, coherent framework. If string theory is correct, it could provide a unified theory of everything, explaining the behavior of all matter and energy in the universe. This would be a monumental achievement, bringing us closer to understanding the true nature of reality. However, much work remains to be done. String theory is still a developing field, and many questions remain unanswered. Researchers continue to test its predictions and refine its equations, hoping to unlock the secrets of the cosmos. As we delve deeper into the mysteries of black holes, multiverses, and beyond, we are reminded of the boundless curiosity that drives human exploration. The quest to understand our universe is a journey that will continue to inspire and challenge us for generations to come. String theory is a beautiful and elegant theory. However, it's also very complex. It requires extra dimensions that we can't see or interact with. And right now, there's no experimental evidence to prove it. Scientists are working hard to find ways to test string theory, but it's a difficult task because the strings are so incredibly small. String theory is still a work in progress. It's possible that it will eventually be proven correct. If so, it could revolutionize our understanding of the universe. Even if it turns out to be incorrect, the search for a unified theory of everything is pushing the boundaries of physics. And who knows what other amazing discoveries await us in the vastness of the cosmos.